for the introduction. And I just thank the organizers, Marcelo and Alas Sam, for inviting me here. And I realized that I'm among
Unmute the mic.
okay. Now fine. Go ahead.
Yep.
Okay. So among invited speakers, I'm the only person who comes from the Asia. So I'm very honored to speak in this very special event for Alex Vassar. Okay, so I met Alex Vassar in 2013 when I visited Austin for first postdoc position. Okay, so at the time I was baby in the field of hyperbolic conservation law because I had a study on some other topic during my PhD program. Anyway, he kindly guided me, and he's like a light to me, and in a very murky situation. But anyway, he was too busy to reply my email, and usually the late reply from my email. But yeah, I'm okay. But thing is that he's very kind. That's it. Anyway, he suggested me at the time. Although I was a baby, but he suggested me very big open problem. That is in mystery me from Navier-Stokes to Euler. That is what I'm going to talk about today. Okay. Still, I'm 9 years old in the in the field of conservation law. Okay. Okay. So this is a compressible Euler system. Already Kang Chen talk about this, and Yu-Chang Chen talk about this system. So compressible Euler system heavily depends on based on the thermodynamics. So here is I'm sorry. The last equation is energy conservation law. There is a first law of thermodynamics. And thing is that we have to consider second law of thermodynamics, which is we have to single out which solution is physical one. Okay. But this original compressible Euler system has a lot of equation and a lot of unknowns, right? So that's why mathematician in fluid dynamics, we try to study on this simplified version for compressible Euler system under very special regime, so-called barotropic regime. That is just the pressure depends only on the density. Okay. So especially we are very interested in the case of polytropic gas. So there is just pressure. The pressure is a function of root of gamma this way. So the law. So here's if gamma equal to 1, then there is a corresponds to the isothermal case. So if gamma greater than 1, then there is so-called isentropy Euler. So, but the thing is that we have very special number, gamma equal to 2. In this case, this model can be used in the modeling of shallow water waves for incompressible fluid with free boundary. So if we model the shallow water in river due to some dam breaking, then this is very useful. Okay, but in practice, I never thought about this one, but in nuclear physics, astrophysics, the pressure still follow the barotropic regime, but this is not monotone in rho anymore. So it's very hard to study on this one theoretically. Okay, so the compressible system, the main feature is, although we consider smooth initial data, but mostly we have the singularly infinite time from the smooth solution. So there is especially shock waves, occur, the shock waves is very singular, very severe singularity because it is a jump discontinuous in space and irreversible in time. Okay, in order to understand the shock formation in 19th century, Riemann is first mathematician. He's a theoretical study on the shock formation. He constructs self-similar planar shock waves, and in mid 20th century, Peter Lux generalized the Riemann shock. I mean, the self-similar shock waves in the setting of hyperbolic conservation law, and he suggests some initial configuration from which shock waves occur. Okay, and this is only for 1D case, but for multi-D case, in 1985, Seidel constructed some initial data from which the shock occur, but by using some contradiction argument. Okay. After that, Christophe Deleuze study on this shock formation in the setting of relativistic setting, and Jonathan Rugg and Speck also consider some construction of shock waves. And recently, Buckmaster and Schuckler, Bicol, and Theodore Ribas, they consider very special shock formation and gives a very special information for flow of time and flow of some position, etc. Okay, so what I'm going to talk about, I'm interested in the stability of shock waves. So what is the stable shock? I'm not an engineer, but so it's we are easily observe the stable shock, okay, in practice. If you look at this flight, so if a flight flies at a supersonic speed, then we can observe this kind of thin cloud near the wing. So this is shock waves, okay? And also we can observe these shock waves, this transparent surface, when we look at the explosion. Then the thing is that this kind of shape of shock waves is maintained for a certain time, right? So that is linked to the stability of shock under physical disturbances. Okay, this picture is what I'm going to talk about. Okay, so before going to the physical disturbances, I'm going to mention some results for stability of Riemann solution. Riemann solution means self-similar solution containing, what I'm interested in, shock waves, okay? Self-similar solution containing shock, okay? So the stability of Riemann solution containing shock at the level of Euler, we have, so okay, first of all, if we consider multi-D Euler and we only consider entropy solution class, then the shock is unstable, okay? So by using the convex integration method, then we can construct infinitely many entropy solution, which comes from the one single shock wave, okay? So ill-posed. But if we consider so only one case, then Guichang Chen and Friedrich Lee, they consider the class of locally VV entropy solution, any large entropy solution satisfying locally VV regularity. Then under this class, shock is stable, but this is conditional because we are not sure whether this regularity propagates in time. Okay, so far no one proved this regularity propagation. Okay, so as long as the solution satisfying locally VV regularity, then we can ensure the stability of shock. Okay, so after that, Alex Vassar introduced the weak notion of locally VV regularity. There is a so-called strong trace property. So if we consider the class of entropy solution satisfying strong trace property, then Riemann shock is stable in this class. And again, this is conditional, except for gamma equals 3. So gamma equal to 3 for the isentropy case in 1D. Alex Wasser in 1999, he proved that strong trace property propagate in time globally. Okay. Am I right?
Yeah, but actually, there is no result of Williams Goldie trying to push in this because it was only in time. But,
Okay. So anyway, it's essentially conditional so far. Okay. So now, not only to achieve the unconditional stability, but also we consider physical disturbances. We may use Navier-Stokes solution, Navier-Stokes flow. Okay. So if we believe this sentence, then this challenging problem would make sense. So real fluid near the shock is still viscous, but the strength of viscosity is extremely small. Okay. Then if we want physical disturbances near the shock, we should consider Navier-Stokes flow. Okay. In the sense of inviscidity. Okay. So challenging problem is that shock wave would be stable in the class of vanishing viscosity limit from Navier-Stokes. Okay, so in order to understand the stability of Riemann shock under physical disturbances, the first step is to consider entropy shock. Okay, so of course our Riemann shock should be entropy. Okay, so which means so Riemann shock is an entropy solution, self-similar entropy solution, which means a weak solution satisfying this entropy inequality. Okay, so Riemann shock looks like that. So Riemann shock is very simple. It's connecting two different constant state as a single jump at the plane and at the plane. And here in time-space coordinates, then this shape propagate in time. Okay, it's a traveling wave solution. Okay, so move at the sigma speed here. And I think I'm missing here the entropy condition. Okay, so this two-end state and sigma satisfies the Rankine-Hughes condition and entropy condition. Okay, that's why the Riemann shock is an entropy solution for that. So okay, so with the Alexis, we get some first result for that. So Riemann shock, as long as shock strength is small, so we call it the weak shock. Okay, Riemann weak shock is stable under physical disturbances. So we only consider a 1D isentropy case. Okay, so 1D isentropy case. So here we only consider continuity equation and momentum equation, and so this is associated Navier-Stokes equation. Okay, so is a new is a vanishing viscous parameter. And okay, so but in our result, just for technical reason, we only consider logic system in mass Lagrangian coordinate. Okay, then so our result cover the gamma greater than 1 isentropy case, and also we consider degenerated viscous coefficient. Okay, so here the mu depends on density, alpha greater than 0 and gamma between alpha and alpha plus 1. And our system, our case contains the shallow water model. Okay, so this due to some some Potham result, then in the class of shallow water model, the gamma equal to 2 and the viscous power exponent is alpha equal to 1. Okay, so our assumption satisfies this spatial model. Okay, so then under this assumption, then our Riemann shock with a small amplitude is stable in the class of Navier-Stokes from Navier-Stokes.
Question?
Yes.
So the initial data for the Navier-Stokes, is that a mollified initial data?
Yes. So, but this converted to this one.
Why not choose the initial data to be the same?
Because we want to get some strong regularity. We need a strong regularity for the Navier-Stokes. Okay. So that's why I saw some actually two reasons. One is to get the uniform estimate. So our estimate should be uniformly with respect to the nu. Okay, so that is the first reason. So that's why we want to choose the spatial approximation. And second reason is we want to assume that this is a smooth, okay, smooth enough to get the smooth solution for Navier-Stokes. Okay. So in the proof, I will show you why we need. Okay, so in order to construct a shift. Okay, so this is a rough statement, but more precisely, if we consider Riemann shock with a small amplitude, small jump, then let's consider nice smooth approximate of our initial perturbation. Okay, so let's consider initial perturbation U0 around the shock. And we want to consider a viscous approximation of this one. Then, and let's assume this is satisfying certain H1 or H2 regularity. Okay, not too much, but and then there exists a unique Navier-Stokes solution with this initial data. Then we can construct the Navier-Stokes limit. Okay, there exists the Navier-Stokes limit from this Navier-Stokes solution. And this Navier-Stokes limit satisfies this stability estimate. Okay, the distance. So this eta is entropy. Okay, so relative entropy. The distance between Navier-Stokes limit and shock, Riemann shock, is explicitly controlled by initial perturbation. Okay, up to shift. So non-trivial time dependent shift. So that's why then we from this stability estimate we say the shock is orbitally stable or stable up to shift in the class of Navier-Stokes. Okay, from the Navier-Stokes. Okay, thing is that this shift can be controlled by initial perturbation. Okay, so as a corollary, our shock is unique in the class of Navier-Stokes. Okay. Okay, so what is the key idea for the proof? Okay, first step is to just the simplicity. First step is to normalize the Navier-Stokes system as nu equal to 1. Okay. Then we should prove that our largest solution from the viscous shock. Viscous shock is a viscous counterpart of the Euler shock. Okay, Riemann shock. So we have to show that any large perturbation from viscous shock at the level of nu equal to 1. So this large perturbation decreasing in time. Okay. So that is so-called contraction. Okay. We have to show that contraction of any large perturbation from the viscous shock. Okay. Then once we prove this one at the level of nu equal to 1, then still this contraction estimate is true at the level of nu. Okay. By rescaling, then still we have contraction estimate at the level of nu. Okay. Original Navier-Stokes. So the distance between our Navier-Stokes solution and viscous shock controlled by initial perturbation. Okay. So then the next step is to get some recompactedness for the solution. Okay. So this is not bad because viscous shock depends on nu, but this is controllable because viscous shock at the level of nu, then this transition zone width is nu. So this viscous shock converges to the Riemann shock as nu goes to 0 in any LP space. Okay. Okay, then first, the first step is to just passing to the limit, this guy, by truncating, stably truncating the solution, okay? Then just passing to the limit, this guy. Then, okay, then still we have the contraction estimate for the solution. Okay, then this is now right-hand side is independent of the nu. Then we have the uniform estimate for the solution, okay? So our solution is uniformly with respect to the nu, okay? Then we have some weak compactness for that. Then we have we can get some weak limit from this solution, okay? So then we can ensure the existence of implicit limit, okay? Then still the implicit limit satisfies the same stability estimate because our distance comes from the relative entropy. So entropy is strictly convex. Then we have some weakly reverse semi-continuity estimate, right? Okay. So then that's it. So this is the whole story of our proof. But the thing is that how to prove the contraction for any large perturbation from viscous shock at the level of nu equal to 1. Okay. Okay, so the basic metric comes from the relative entropy. Okay. So in order to measure the distance between the largest solution and shock, we need to use we want to use the relative entropy because already Ben Chen talked about this one. So relative entropy behaves like a quadratic distance locally, but if we consider any large perturbation, then this is very nonlinear. Okay, heavily depends on the convex function. I mean the entropy function. Okay. Anyway, this is positive definite, and so from the relative entropy method by Thomas de Ferena, and we have this form. Okay, so the time evolution. So okay, first of all, if we write down our Navier-Stokes over Euler in this hyperbolic conservation law form, okay? So this is the viscosity and this is Euler, okay? Then the time evolution of relative entropy between any two solutions, okay? Even this is true for Navier-Stokes Euler, okay? Then this guy equal to the divergence of some relative entropy flux, okay? This is a sort of the cubic perturbation of U and V. And this guy plus parabolic term, okay? If we consider the Euler, then just we have this structure. Okay, then from this one, we get, it's very easy to see that constant solution, constant state is just stable. Constant solution is stable under any large perturbation. Because if we consider constant vector V here, then this guy is 0, right? And integrate in space, then this is a finish, right? And then we have time derivative of space for relative entropy is decreasing in time, right? Okay, so then constant state stable under any large perturbation. Then this would be useful to us because we want to control the Riemann shock, right? The Riemann shock connects two different constant states, right? And this would be useful locally, but it's a very murky situation because shock is not, very singular stuff, right? Okay. Anyway, so under this, using this topology, then we want to show that our large perturbation is contractive, orbitally stable. So we need some dynamic shift, and for the Navier-Stokes, we need to introduce the weight, as mentioned, as Chen mentioned. Okay, so if you I want to give you some intuition for this method at the level of viscous model. Okay, so for the viscous burgers, okay, toy model. Okay, so let's consider, just for simplicity, let's consider concave flux for viscous model. Okay, the burgers model. Then let's consider some traveling wave solution, stationary traveling wave solution, connecting 0 to 1. Okay, so this is a physical shock, and we want to construct a shift. Okay, just to put the shift here inside the shock. Okay, and we want to consider quadratic entropy. Okay, you see the scalar equation has, for the scalar conservation law, any convex function is entropy. Okay, so it's a very nice option. Okay, so we want to choose quadratic entropy because our flux is quadratic. Those are consistent, right? Okay, then just to take the time derivative after integrating in space. Then we have some shift part, right? And this comes from the bogus flux, and we have diffusion. Then we see this diffusion cannot observe this spectrum, right? But if we define the shift stably, then we can make those guys to be observed into the diffusion. That is just a Poincare type inequality. Okay, so this kind of Poincare type inequality within mind. Okay, so the thing is that every spectrum localized by derivative of shock. Derivative of shock behaves like a probability measure, right? Okay, so this quadratic perturbation localized by the probability measure, and also this is just the average of the perturbation. Okay, so then if we define the derivative shift like a negative this average, then negative squared this average, and combine together, then we have this variance. Okay, so f is a perturbation, and the derivative of shift localized. Okay, then diffusion after using the y variable. So y is just the. I'm sorry.
I have a question.
Yep.
Why don't you just use the Burgers flux? Why do you use u1 minus u?
This is just a simple. Otherwise we have to approximate this
I see.
some Jacobian from the diffusion.
I see.
Okay. Anyway,
I see.
yeah. Then by using this variable, then actually dy over dx is just y minus 1 minus y. Okay. This is very generic. If we consider other
But then this is a little harder.
Yeah. Anyway, then our right hand side is negative. So viscous shock in for the Burgers is contractive under any large perturbation, right? Okay. Yeah, the thing is that in this Burgers equation is very special. So because the given the flux is quadratic, then we choose the spatial entropy. That is a quadratic, which is consistent with the flux. Okay, that is magic. But in general, it is we need some more sophisticated estimate to get a contraction, even for scalar. But for the system, for the Navier-Stokes system, the thing is that Navier-Stokes system has a diffusion only for the velocity variable, right? So no diffusion for the density. Then eventually we want to apply Poincare type inequality, but any better term, and even no matter what the shift is, we have some crossing term. Okay. So this is pressure is a function of rho, density, and velocity. So no way to control the density term. Okay. So no diffusion for the density. So then that's why we want to introduce the weight function. Then we observe the structure of the hyperbolic conservation law. So if we consider, this is a 2x2 system, okay? Then we want to use this fact, okay? So the shock speed times derivative of density wave always positive. because one shock, if we consider one shock, then in the Lagrange coordinate, then sigma is negative, then the density profile is decreasing. Okay. Anyway, this is a very nice structure. Then we define the weight function that is just derivative of weight proportional to the derivative of density profile. Okay. Then here, if you take the time derivative here, okay, the shock speed, then minus sigma comes out and a derivative, and relative entropy is positive definite. Then this is good term. So this is, we can get some additional good term thanks to the weight function. Okay. So then, but still, this is not enough for this guy to observe the bad term concerning on density. But instead, we just maximize all bad term concerning on the density. Okay. So using this good term. Okay. And then we just decouple the density and the velocity, and then we only eventually everything boils down to show that is enough to control this term concerning only the velocity field using the diffusion for velocity field. Okay.
I have a question.
Yep.
Is A piecewise constant like with Benchen, or is it smooth?
This is smooth because now A is PX like a physical shock.
Okay.
Yeah.
The analogy works.
Yeah. Viscous counterpart of the invisible drum. Yeah. Everything. Yeah. Viscous counterpart. Okay. So but this is a very short overview for the proof, but compared to the Burgers case, our flux is very not quadratic, right? Pressure is very nonlinear, right? And diffusion very simple. But so that's why we need to define the shift very carefully. So idea is that if y is not too small, then we may define the shift such that this swallow this vector. Okay. Otherwise, if it's very, very small, then no way to prove directly, right? Okay, because this is degenerate. Okay, so then this is our construction. But in order to define the shift, so in order for the instance of shift, then we need some regularity for the solution for Navier-Stokes. Okay, so this is comes from this is dynamical shift, right? Okay, so that's why in order to guarantee the existence of shift, we need some regularity, but not too much, just a strong solution.
So to come back to that point, so the initial condition being smooth is playing a role here too.
Yes. Mm-hmm. Yeah. Sure. So initial density has a low bound from below and above. Okay. And L infinity H1, something like that. Yeah. Then okay, so this actually, in order to guarantee such kind of regularity, we heavily use the Peter constant result for the parabolic case. And I'm sorry, the periodic domain. So we extend the case of periodic into the whole space, connecting two different points. Okay. And now then, it remains to prove that if the y part, shift part is very, very small, okay? Very, very small, then from our construction, then our shift part becomes like minus y functional square, okay? So it remains to prove this main proposition. So actually, in order to this main proposition, at the beginning of our proof, we would better use the Desjardins entropy, because our flux is very nonlinear, which is only depends on density, right? But diffusion is a velocity. Okay, so that's why we want to use the Desjardins entropy to transform our original Navier-Stokes to this model. Then now we have diffusion with respect to the density. Sorry, here is V is density. Okay, specific value 1 over all. in Lagrangian coordinate, okay? So then we have diffusion for the density, V, and so then we would control the pressure here, right? Because in the Lagrangian coordinate, the velocity field is linear. H is Brechstedt velocity, okay? U frame, the U effective velocity field. Then this is linear, then much easier to control this one compared to this pressure term. Okay, then just now, then the game is to use the Poincare type equality for the V variable, density variable. Okay, then just truncate with some small parameter, which is far bigger than the small string, short strings, but still very, very small. Then just tail expansion for this, for such a V variable pressure near the shaft. Then we have some, and normalization, then we have some very nice form. So actually we can show that this is decreasing, okay? So it's kind of nonlinear Poincare type equality with the constraint. Okay, then if this perturbation is very big, then we can use this assumption. So our y functional is very, very small. Then what it looks like, y functional is the derivative, integral a derivative relative entropy plus this linear perturbation. But this is a sign because a prime always negative or positive. Okay. So then if y very, very small, then this would be very, very small. Okay. So then localize the energy very, very small. Then this is very useful in controlling the outside of truncation. Okay. So this is the proof of our theorem for the case of one shot. Okay, single shot. What if we consider the Riemann solution composed of two shots from different family? Okay, then our answer is yes. Our Riemann solution composed of two weak shots, still orbitally stable in the class of implicit limit from the Navier-Stokes. So we consider two shot. Okay, one shot and two shot. The thing is that okay, at the level of Navier-Stokes, the viscous counterpart of the Riemann solution composed of two shot is not solution to Navier-Stokes anymore. Okay, so Euler shot looks like Euler one shot plus Euler two shot minus intermediate state. Okay, but if we consider viscous counterpart, then this converges to the one Riemann wave, and this converges to two Riemann wave. But at the level of Navier-Stokes, this is not solution. Okay? Then, but the thing is that if we construct two shifts, one is for one shot, the other is for two shot. Okay, we need to define the two different shifts like x1, x2. Okay, here. So now in our viscous shot, this guy move along this trajectory, this shift, dynamic shift, and the other two shot moves along this x2 trajectory. Then if we can construct two shifts such that those are well separated. Okay, this is very well separated. So this is picture. Okay. So this is the original trajectory for Riemann solution. Okay, just perturbed by the dynamic shift, but still two shifts well separated. Okay, then our viscous shot, this is the viscous shot with zone, the transition zone nu. So we take the nu very, very small. Then this is very sharply decreasing. Then this wave move along this trajectory, and two viscous shots move along this trajectory. Then the interaction between two waves almost negligible because the viscous shock approach two end states exponentially fast. Okay, so then the interaction, this interaction between these two viscous shocks is negligible, okay? And also integrable in time. So eventually we have this one. Okay, so the distance between Navier-Stokes solution and our shifted viscous counterpart of the Riemann solution controlled by initial perturbation plus error term, but this is goes to zero as nu goes to zero. Okay. Okay. Then this is very crucial to generalize in studying on the general Cauchy problem. Okay. So now under some additional assumption, then with Kang and Vassar, we show that entropy solution of small BB entropy solution are stable in the class of invisibility from Navier-Stokes. Okay, the key estimate for that construct already the Kang talk about this one a lot, but okay, so construct viscous version of front tracking approximation. Okay, so the distance between Navier-Stokes solution and approximate by front tracking algorithm. This guy controlled by initial perturbation plus certain error depends on nu, and delta is some numeric parameter. Okay, so delta goes to zero and nu goes to zero. Then this constant will converge to zero. Okay, so we want to get this estimate. Okay, in order to show this one, so what is the contribution of this one? So now from this our construction, the one family wave never reach the two waves from the left. Okay. So then this is very important to control the Klein potential. Okay. Okay, but compared to the Wheeler level, still we have a very many obstacles because we have no uniform bound for the Navier-Stokes. Even for 2x2, we have no maximum principle, right? Okay. So we cannot get any LNP bound and any uniform bound for the Navier-Stokes. And in the front tracking algorithm, the number of front now depends on the nu. Badly depends on the nu, right? Okay. So this is the main difficulty. So now, okay. So let me start with this. This is some last remark for my. So I want to emphasize our method is very robust. I mean, we can apply our method to other contexts. So first of all, if we want to study on the long time behavior of Navier-Stokes solution with small initial perturbation from the Riemann data, then we have we can apply our method to this problem. Okay, this is very I mean long-standing problem since Oleinik in 2050. Okay, so we apply the method to the case of Riemann solution composed of shock and rarefaction for the one developed in Navier-Stokes. Okay, so then this Navier-Stokes flow would converge to the viscous counterpart of our Riemann solution. Okay, viscous shock and rarefaction. Okay. So anyway, I won't talk about more detail, but anyway, so the thing is that if we consider small perturbation, then we can get some more result. So even we can get some result for the Navier-Stokes Fourier system. Okay, we can get some long time behavior of Navier-Stokes Fourier flow perturbed from Riemann data, generating generic Riemann solution. Okay, shock, rarefaction, contact discontinuity, and also we can apply our method to multi-D problem as long as we consider small perturbation. Okay, so multi-D and even recently with my students, we recognized our method is still robust in studying on shock waves, stability of shock waves for quantum response 1D. Okay, viscous profile. And last remark is for we can apply our method to the some viscous conservation law arising in the chemotoxicity model. So we can show that viscous profile arising in this model contractive. I mean, any large perturbation of viscous profile for this model is contractive. Okay, and we can show that the existence result for that. So this is joint work with Yudong Choi, the former student of Alex Vassar. And okay, so happy birthday, Alexis.